So my name is Joey. I'm leading the open source toolchain team within ARM. Today I was going to talk about the optimized routine. So why we talk about the optimized routine here? It starts with a problem that we've been facing for a long time. You know that both ARM and the ARM partners have been contributing a lot of library functions, optimizing the libraries and contribute to upstream projects. But what used to happen is like a developer one, engineer one, contribute something, a math function, contribute into glibc math library, and the similar math functions can have another implementation, contribute to Android, and there's another memory function, contribute to glibc, and so on and so forth. So each individual engineers have their own implementation of certain functions and upstream them into different upstream projects. So there's problem in such a model. The first problem is the reusability. Because of different projects are separated, the same implementation cannot necessarily be shared across multiple open source projects or across open source project and a closed source project. So there's fundamentally something that can be reused by another project, just cannot be reused from the existing implementation. So that is the problem of reusability. But looking behind why the reuse doesn't happen, it was caused by lack of visibility. Because nobody know, a lot of times nobody know there are existing libraries, existing functions, implementations, optimized, exist, can be found somewhere. So they have no choice but reinvent the wheel by themselves and have another implementation followed by another. Just this week on Tuesday, I was talking to some people from COSS. And they were talking about something in the library domain, some open SSL function, crypto function, something like that. Some of them realized, okay, yeah, they actually doing this very similar things, but and they never know that the other party are doing implementing the similar things. They've never realized that there's a possibility for reuse. So yeah, it ends up with a lack of reusability, and at the bottom of it, there's no visibility of the existing contributions. So how to resolve the problem? A natural solution is just have one library, or else say a centralized library space, so that people can always go somewhere to find if there are existing implementation for certain functions. And if yes, then they can contribute, they can reuse directly. If no, they can just contribute and put their implementation there so that someone else can reuse them in the future. So that's a straightforward idea. So if it is implemented, it will be working like this. Then there will be a centralized place we call the optimized routines, and in that the centralized place or centralized projects, they are like math functions and memory functions or whatever functions that are grouped by the functionality or the use or the nature of their functionalities. And from there, those functions can be further propagated into upstream projects like glibc, like Android Bionic, like NewLib, or even some of them can end up in Microsoft because they can use them as reference code. It will be published with a very liberal license, so people can just reuse them with no limitation. By doing so, the memory function, certain memory functions need only be implemented and optimized once, and they can be used in a number of upstream projects later. So given that's the idea and how to implement it, here is the first step we have accomplished. It is a GitHub project called optimized routine, and it is in the subdirectory of ARM software. And it is a library functions license under MIT, which is a very liberal license, but we need a contribution agreement, the on-copyright contribution agreement, so that the copyright can be assigned to ARM, and then ARM can take those code further into projects who need the copyright assignment, like glibc. Without copyright assignment to ARM, the ARM cannot bring them forward into upstream project like glibc. Also in the contribution agreement, it is allowed for the original author of the contribution to contribute directly into upstream project like glibc. So there are two ways. If contributed into optimized routine, either an ARM engineer can contribute further, or the original author can contribute the same code into another project which need a copyright assignment. So yeah, that's the whole purpose of a copyright assignment, is enable everyone to take the code into this project and contribute further into a wide range of upstream projects. And currently the project contains math functions, I'm going to show a table, and memory stream functions. It was right to point out that the math and the stream functions were merged from original Cortex Stream project with the help from Adam Melville and linear engineer. Thanks for the support from the linear toolchain working group to make the merge happen. That's a very good achievement that actually makes sure that the math functions and the stream memory functions are hosted in a centralized place. So that's the whole idea. You just need to go to a centralized place. You don't want your users to check multiple places, or check whether this library have something, that library have something, that place have something. So we put everything together, put them into a centralized place, optimal routing, and yeah, to find out whether there's something that you can reuse. That's our idea. We achieved this by the first step of contributing the math functions and merge the other memory stream function project together. So moving on, there will be no need of updating the Cortex stream. Everything, if you can find, then should be found in the optimized routine project. With this model, we have been already very successful propagating those contributions into upstream projects like math functions. We migrated math functions into glibc, newlib, and bionic. Especially merge the math functions from optimized routing in the bionic help to achieve significant performance improvement on Android benchmark like Geekbench. That was also done by a linear engineer. It was very helpful on this. Another usage is to propagate the function in this project into commercial compilers. ARM has called the ARM Performance Library. It is like a commercial library project. It can also take the code from this open source project and deliver in their commercial product solution as a total solution. So yeah, so this is basically with this project you can propagate, you can reuse in your open source project. You can also reuse in not necessarily say closed source project. take a closer look at the optimized routine project. What does it have now? As I mentioned earlier, it has math functions, it has string and memory functions. Here are the rough list of the functions in the math and the memory and the string. I didn't include everything. Say, for example, there's a cosine function, but they're actually cosine and a cosine f, and the expo, the expo f, which we're targeting for double position and the single position. But basically, the actual list has more, but I just list the functionalities here. You have a sine, cosine, have expo, have log, and the power, those kind of functions. And the string memory side, we have memory char, memory copy, memory move, and the counterpart of string version, like a string length, string copy, those kind of thing. You probably noticed that all those functions are defined in C library. So that is the focus, that is our focus now. We have been focusing on optimizing C functions. Those are all C functions. Of course, in the future, we definitely can extend into non-C functions. As long as there's value to be reused, to be shared in some place, then we are open to them. So moving on, we are going to keep adding new functions into this project. What we are currently doing is add the vector math function into optimized routine. So vector math function is the vectorized version of those functions I mentioned earlier, which means that you can take vectors as input, and after the calculation, take another vector as output. It can maximize the opportunity of vectorization within the implementation. So that will give a significant speed up if the application can be optimized that way. So that's something going on. We're going to upstream the code into optimized routine, the vector math function into optimized routine first, and then from there going to places like glibc and other things. At the same time, we are optimizing some other memory and string functions for the latest architectures. The memory string functions listed in the previous table, some of them was contributed years ago. They were targeting, when they were implemented, they were optimized for the certain CPUs that were dominating at that time. Now we can actually use more microarchitecture and architecture features to optimize those functions for the later CPU. So those are the things that we are doing. A lot of things need to be done because given that a number of C functions, memory functions in the C library, numbers are huge. And also given that the number of CPUs in the market, number of ARM CPUs in the market, multiply this by then create a matrix that can be a huge number. So we only focus on important functions and important architectures. So that is the plan. Of course, everyone are welcome to contribute. So what I'm going to call for action for everyone in the Linaro, in the ARM ecosystem, everyone. Firstly, to try to reuse as much as possible. So whenever you have a need of some new functions, need the optimized version of certain functions, go this place, check out this place first, before you spend your precious engineering resource to have your own implementation. So it's fine that the existing optimization here is not optimum. You can keep improve it, or even if you decide that you need to have a new implementation, please contribute back into this object, this project, so that others can benefit from it. Others don't have to re-optimize, re-implement for themselves. So first step, reuse. Make sure that I check it out, reuse it. If not, contribute and contribute back. Develop and contribute back so that the others can benefit. And furthermore, extend the scope of this project. So far, we only have math and the stream, and we already have a talk with the gentleman here. I was talking about something related to open blank, and there's another conversation related to open SSL. So all those functionalities can actually be put together into this project with just some bit structure, creating new directory, for example, and creating a new sub-project beneath it, for example, so that the project can grow more and more, and the chances of a reuse can be maximized. Yeah, so that it can be a centralized place for anything that can be shared, can be reused, and your contribution will be multiplied. You're not only developing for yourself, your optimization, your implementation is going to be benefit the whole ARM ecosystem. So that's the whole purpose of this project. I think that's all the slides I have. It's time to take some questions.
Okay, I got maybe say 2 questions. The first one is, so I saw you have put some plan here, so that would be great. So do you have some kind of roadmap or something which we can find in the GitHub?
There's no written down roadmap. We do have an engineering plan. Yeah, probably there's something we can do better sharing the roadmap. We do have some plan like optimizing the vector math. It will be roughly work out probably next year, sometime next year. And at the same time, we have some memory functions plan to optimize here and there. But yeah, there's no formal roadmap that can be shared or published.
Okay, so another question is, I know that there is a compute library also hosted by ARM. So in terms of how to say it, math-related functions, so what's the difference between these optimized routine and comparing to the compute library?
So this, as I mentioned, so far has been focused on C libraries. Yeah. So the compute library, if it's say still also targeting CPU optimization, if it's also targeting say multiple upstream project, we will be open for them to probably put together, put 2 projects together so that they can be a sub-project under these project. The whole idea is to have a centralized place so that they can increase visibility so that everyone know where to find if there's something that can be found.
Okay, thank you.
Welcome.
Thanks. Is this working? Okay, there we go. Just wanted to add 2 things. So I didn't see any performance numbers in your slides, which is surprising because the performance is actually extremely good. So I use these optimized routines almost on a daily basis. In fact, I was recommending this morning somebody should use them. in real world applications, you can see a 2x speed up just by changing your link line. They really make a difference, so it's worth using. The other point is, you say that they're in glibc, but that doesn't necessarily mean they're on your system. So for example, I'm working with systems that are on something like a RHEL 7.2, which means it has a libm 217. So these are not default, what you get from the libm. So it's very much worthwhile to go to GitHub and use these if you think you can get better performance in your math code. It's very worthwhile doing it.
Yeah, thanks, Sean, for the comments.
So if they're not in RHEL 7, you should probably make a request to have them incorporated, because routines like this get backported very regularly.
I'm sure that conversation is going on. It's, yeah.
Because this was like 2 years ago, so.
Yeah. So Masters famously told us that it's easier to change the hardware than the software when it comes to this kind of stuff. It's a conversation. Point is, at least if you're writing applications, grab the stuff from GitHub, because that's what works.
Cool. So at least for glibc, I can assure you that it'll be easier. If in most cases, it would not be an ABI change. So since it's not an ABI change, it should be easy for you to get stuff in.
That would be awesome. I would love to see that.
Any other questions? Okay.
So are the performance numbers put up somewhere so that we can compare before, or do you just go through the code and figure out what's the complexity and go from there?
So all I can say is that those performance, implementations are far better than the existing or than the original glibc implementation. Those numbers, yeah, they were published in somewhere in the glibc community or some also. Yeah, my recommendation will be just download the source tree, build by yourself, and try to measure in your application. That will be the best way to measure whether it is going to be helpful for your application or not. It might be that some functions being optimized like by 10 times, but your application just use it once or twice. It doesn't really help you. So it all depends whether your application is going to be benefited from this project. So yeah.
So I think I can answer your question regarding the performance numbers. Sabolch had done a talk at GNU Tools Cauldron. I think this was in Prague, right? The math functions.
Yeah.
So that has some initial numbers. I don't think all of the functions that were implemented had conference talks for each of those. But then that is one source. The other source would be the glibc commits. We strictly require people to specify what kind of improvement they see with every single change that they make. So if you look for, I guess there are 3 or 4 people who have done this work, not a lot more than that. So if you look for specific ARM architecture improvements in string functions or general improvements in math functions, you should be able to find all of that information. But it's not as easy, for sure.
Cool. Okay. Looks like time's up. Thank you very much for coming to this session. Thanks.